Could we colonize Alpha Centauri today? In history, nuclear bombs have only been used as weapons of mass destruction that endanger all of humanity. During the 1960s, when these weapons proliferated, some scientists proposed a revolutionary idea to put these devices to non-destructive use. The idea was to use the growing number of atomic bombs as methods of propelling spacecraft, thus giving rise to the creation of a method of space propulsion known as nuclear pulse propulsion. This method would use the power of atomic bombs to propel spaceships and, according to some scientists, could even help us get out of the solar system, as this method would allow us to reach high speeds in very short periods. This new propulsion method was tested in several experiments, proving so efficient that NASA planned a trip to Mars using this system, reducing the travel time from 9 months to just 3. This method of spacecraft propulsion was not developed due to various factors. Still, if it had been developed, it is possible that today there would be colonies of humans on Mars and even on Alpha Centauri. But why wasn't this technology developed? Was it really that efficient? And how would this propulsion technology have helped us get to Alpha Centauri? Join us to find out. Using explosions to move a vehicle was not a new idea for the 1960s. As early as the late 19th century, Hermann Ganswindt and R.B. Goskowski proposed using explosives to move all sorts of things. But it would be during World War II that the definitive explosive device would appear, the atomic fission weapon. In the post-war period, advances in the design of missiles would allow us to dream of space travel, just as Jules Verne dreamed of them in his famous book, From the Earth to the Moon, a century earlier. The true father of the concept of space propulsion using nuclear explosions would be Stanislaw Ulam, a young mathematician of Polish origin who worked in the laboratory of Los Alamos, New Mexico, as part of the Manhattan Project in 1944. Like many other scientists like Oppenheimer, Ulam's research at Los Alamos focused on developing the first atomic bomb. In time, Ulam would become eminent in this field of human knowledge. He would be one of the creators of the famous Teller-Ulam design for staged thermonuclear weapons, better known as fission-fusion weapons, or hydrogen bombs. But in addition to devising weapons of mass destruction, the young Stanislav calculated that the tremendous energy of a nuclear explosion could be used to propel some kind of spacecraft. In 1946, just 1 year after the explosions in Hiroshima and Nagasaki, Ulam conceived, together with a colleague from the Manhattan Project, Frederick de Hoffman, the first concept of nuclear pulse propulsion. Reynes and Ulam would refine this idea the following year. During the nuclear explosion tests, Ulam verified that some metallic elements survived the explosion more or less intact thanks to the ablation mechanism. If a spaceship were equipped with a flat metal plate that reflected the energy of the explosion, it could perhaps move at enormous speeds using atomic explosions. This concept presented an obvious obstacle. More than half of the energy of the explosion was lost in space. Only a tiny part of the shock wave would intercept the propulsion plate. It seemed more efficient, though more complex, to contain the explosion in a nuclear combustion chamber, and thus harness almost all the energy. Ulam was convinced that nuclear propulsion could take us to the stars despite all the obstacles. Thus, in 1955, he presented, together with Cornelius Everett, a refined version of his original nuclear propulsion project. This project appeared in a paper that used the results of Inuitox tests to demonstrate the advantages of its design. According to his calculations, the booster plate concept would be much more efficient than the combustion chamber concept and far superior to conventional chemical rockets. As a result, he proposed a 12-ton spacecraft with a plate 10 meters in diameter that could travel throughout the solar system. This craft would need between 30 and 100 little nuclear devices to move. The plasma formed by the vaporized remains of the bomb would be intercepted by the plate, which would transmit the thrust to the vehicle through shock absorbers. Such a plate would comprise several disposable disks that would function as fuel. The most complex part of this concept was to take off from the Earth's surface using nuclear explosions, but Ulam believed it was possible, and in 1959, they would patent an improved version of the vehicle in the UK. Propulsion systems are classified using two main parameters, thrust and specific impulse. Thrust is nothing more than the force that develops the engine. The thrust generated by a nuclear explosion is thousands of times greater than that of chemical fuel. On the other hand, the abbreviated specific impulse, ISP, measures the efficiency of a propulsion system. The higher the ISP, usually measured in seconds, the higher the payload or speed the spacecraft can reach. The most efficient chemical propulsion engines, such as those in the Space Shuttle, have an ISP of about 430 seconds. Pulse nuclear propulsion engines could reach an ISP of about 1,000 seconds, and a spacecraft like ULAM proposed promise to reach up to 1,000,000. But would a spacecraft withstand the brutal jolts of nuclear explosions? And what about radiation? Unfortunately, ULAM was unable to answer these questions. Although he was a genius, it was clear that he alone could not design such a complex vehicle. If you like this video, we invite you to subscribe to our channel so you don't miss the next videos. Following ULAM's ideas, in 1957, a group of engineers and scientists met in San Diego, California, to work on a secret project. They aimed to design a spacecraft that could travel anywhere in the solar system in days or months. This project would be named Orion, after the famous constellation of the Hunter. Orion differed from other rockets because it did not use conventional chemical fuels. Instead, this spacecraft would be powered by ULAM's ideas, i.e., with nuclear bombs that would explode behind the craft, accelerating it to incredible speeds in a very short time. This group of scientists would try to solve the unknowns that ULAM could not solve alone at the time. To find the answer to these questions, we have to travel to Eniwetok, a remote atoll in the Marshall Islands. In this paradisiacal environment, the United States conducted numerous nuclear tests on the surface between 1948 and 1958. In addition to causing severe environmental damage, all kinds of experiments were carried out during these tests. In June 1956, during a test nicknamed Inca, a physicist named Lou Allen had the idea of suspending two hollow metal spheres 10 meters above the nuclear device. The spheres, about the size of a watermelon, were covered with a thin layer of graphite. The blast had a power of 15.2 kilotons, KT, a figure roughly equivalent to the Hiroshima atomic bomb, more than enough to vaporize the suspension cables of the spheres. When Lou Allen looked the site at where he had placed the empty spheres, he thought that, like the wires, they had vaporized, but they had not. After thoroughly searching the vicinity of the explosion, engineers found the spheres a few kilometers from ground zero, in perfect condition. They had lost only 0.1 millimeters of their outer graphite layer due to the explosion. But why didn't the spheres vaporize? This is precisely due to the graphite covering them. This material absorbed the radiation, and instead of being vaporized by the heat, the spheres were simply propelled by the explosion's shock wave without suffering any damage inside. This showed that it was possible to build a spacecraft with a similar material to withstand nuclear explosions. One of the problems of creating a spaceship propelled by nuclear explosions had been overcome. The ship that would take us to the stars was beginning to see the light. Beginning in 1957, dozens of engineers and scientists were recruited by Theodore Taylor for Project Orion, including Freeman Dyson, a researcher who had worked on Project Helios and who would be Orion's leading supporter for decades to come. But in October 1957, the world would change forever. The Soviet Union had launched a small metallic sphere into orbit, thus inaugurating the space age. Sputnik was a game-changer. Traveling to space was no longer a fantasy but a priority. Consequently, the Orion project soon received the attention of the military. In July 1959, the project would come under the control of the Military Advanced Projects Agency ARPA. The team grew to 40 members, with Hoffman as the primary manager. However, after the initial enthusiasm and the rapid advance of the Soviet Union, the Pentagon concluded that Orion was too fanciful a project, so it relinquished control at the end of 1959. From 1961, the Secretary of Defense of the Kennedy administration, Robert McNamara, refused to fund Project Orion. In 1963, the USSR and the United States signed the treaty banning nuclear explosions in space, which meant the political death of Orion, and in 1965, the project was definitively canceled. However, just that year, the Orion team achieved the unimaginable. They proved that the nuclear pulse craft was viable for the technology of the time. According to the research, the effectiveness of the design depended on the size of the fission bombs employed, which in turn dictated the size of the spacecraft's plate. The team created two studio versions, one with a 10-meter diameter plate and one with a 20-meter diameter. The former could be used for trips to the Moon or Mars, while the latter would have allowed Saturn to be reached before 1980. They also calculated the material they would use for the plate, its withstand temperatures, and the cooling system to mitigate heat and radiation. It is known that the team used data obtained in accurate nuclear tests and estimated that an operational Orion spacecraft could achieve an LSP impulse of 1,800 to 3,000 seconds. It wasn't a staggering figure, but realistic and far higher than any current chemical rocket. The small version of the study, with a 10-meter diameter booster plate, could send 8 astronauts and 100 tons of equipment to Mars in just 125 days round trip. To give you an idea, current spacecraft estimate that a trip to the red planet would require 180 days on the one-way trip alone, with a total duration of more than a year. The 20-meter Orion would allow us to travel to Jupiter in 900 days or to Saturn in just 5 years, instead of the more than 15 it would take with modern spacecraft. As if that weren't enough, a slightly larger Orion spacecraft would allow us to not only reach the outermost planets, but also leave the solar system and reach a tiny fraction of the speed of light quickly. With a nuclear pulse propulsion system detonating a 10-kiloton bomb every 10 seconds, it would be possible to reach 10% of the speed of light in less than 10 years. This is equivalent to reaching a speed of 30,000 kilometers per second. With that speed, a spacecraft would reach Alpha Centauri in 40 years. Yes, I know that 40 years may sound like a lot of time, but considering that this star is more than 4 light-years away, and that with modern spacecraft, it would take thousands of years to reach it, 40 years sounds okay. This means that if the Orion project had not been canceled in the past, the first spacecraft with nuclear pulse propulsion would be returning from Alpha Centauri, or we would even have a human colony in that distant solar system. Before we move on to the last part of the video, be sure to stay tuned afterwards if you haven't seen our earlier detailed release on how long would it take us to go to Proxima Centauri. Of course, in the 1960s, it was not known that there were exoplanets in Alpha Centauri, nor did the concept of an exoplanet even exist. Curiously, Orion has been relegated to the darkest corners of the history of the conquest of space. In most works of fiction devoted to space travel, fusion or antimatter systems get all the attention, while the nuclear pulse is considered a mere historical extravaganza. But, with all its flaws, we must remember that pulsed nuclear propulsion is the only advanced propulsion system that would allow us to travel to Alpha Centauri using existing technology. In the 1980s, Carl Sagan declared that Orion would be the best use that could be made of the thousands of nuclear weapons that exist on our planet, and maybe he was right. How long would it take us to go to Proxima Centauri? How long would it take us to go to Proxima Centauri? That of one day reaching out and touching the stars is a relatively recent desire of our species. We can perhaps date its appearance to 1838, the year when the German astronomer Friedrich Bessel first succeeded in determining the distance to a star and clarifying the extent of the problem we faced. A dream, we said, but with recent advances in technological development, it seems that dream is slowly becoming a reality, hand in hand with our growing awareness of the limited resources and environmental problems we face here on Earth. Indeed, stars are far, far too far away. But there you go. If there were an exoplanet with some Earth-like qualities within a radius of a few light-years, not 100 or 1,000, as is the norm, then yes, this could work. It would do a bit like the Moon, which served as a first step, a spur to get us to the other planets. We could start seeing interstellar space as a sea sprinkled with islands, rather than as the current unreachable void. What a pity. But what's going on there among you who are listening? I think I can hear someone tapping on the monitor and protesting. But yes, there is this planet. We've been assured of it since 2016. Well done. This is exactly where I wanted to take you, awakening and measuring your attention. It's true. We have an extrasolar planet very close to us, discovered in 2016, but confirmed absolutely only recently. And that's incredibly lucky since the average distance from Earth of the other 5,000 extrasolar planets is about 300 light-years. A stroke of double luck, since the planet orbits the closest star to Earth, namely Proxima Centauri, a fortune that many are now realizing. So even NASA has apparently decided to go and have a look there by the end of this century, with a project that is finding strong resistance in certain scientific circles, but which the American Space Agency believes it will be able to launch by 2069. A date obviously not coincidental, remembering what happened exactly 100 years earlier. That would indeed be an exhilarating feat, would it not? But where then does anyone's skepticism come from? Well, the immensity of the distance that separates us from Proxima is scary anyway. How can you blame them? Moreover, it is enough to look a little closer at the destination of this trip to immediately realize that going to the moon was like climbing the first step of a staircase that has more than 100 million steps. 100 million, yes, because Proxima Centauri is exactly 100 million times farther than the moon. Alpha Centauri is a system composed of 3 stars: Alpha Centauri A, officially Rigil Kentaurus; Alpha Centauri B, officially Ptolemy; and Alpha Centauri C, officially Proxima Centauri. Alpha Centauri A and B form a binary pair of sun-like stars revolving around their common center of gravity. Proxima Centauri is a red dwarf revolving around the 2 main ones at a distance of about 0.2 light-years and is only 4.25 light-years away from us, or about 40 trillion kilometers. The extrasolar planet we are talking about, called Proxima b, revolves around Proxima at a distance of about 0.049 astronomical units, more than 20 times closer than Earth is to the Sun, but still within the habitability zone. Compared to some other depths of the cosmos, we are basically talking about our own backyard. Yet a trip to Proxima with current technology would take about 78,000 years, an enormous amount of time, calculated based on the maximum speed reached by our fastest probe, New Horizons, which is 59,000 km per hour. If, on the other hand, we wanted to reach Proxima with a journey of reasonable duration of 20 years, a spacecraft would have to travel at an average speed, including acceleration and deceleration, of more than 300 million kilometers per hour, or 28% of the speed of light. Quite a difference, wouldn't you say? In short, NASA will henceforth have the difficult task of finding a faster way and more effective technology to reach at least the stars closest to us. It would require the development of a propulsion system that would reach at least 10% of the speed of light to reach the Alpha Centauri system in an acceptable time. The main difficulty lies in storing the fuel load necessary to enable the spacecraft to be able to accelerate steadily to the expected speed threshold. Despite the seemingly insurmountable difficulties, several interstellar ship concepts have been proposed in the past decades. An early example dates back to studies and experiments conducted in America in the 1960s as part of the Orion project. Basically, the idea was to harness the shock wave produced by the sequential explosion of many small nuclear bombs to accelerate a spacecraft to high speed. The project was originally designed to put large masses into orbit or to enable human missions to Mars, but someone realized its potential for interstellar travel as well. In the original version, the Orion was to eject nuclear fission bombs in rapid succession, which, detonating just behind the vehicle, would give it a substantial boost through the impact of the shock wave thus generated on a special shield, capable of absorbing the shock without damage. A more powerful version, with fusion bombs, was later suggested by British physicist Freeman Dyson, but it was soon overtaken by technological advances and the changing political climate. However, this concept, which would solve several of the problems discussed above, remains suggestive and could be applied to launching small probes to the stars. In those same years, American physicist Robert Bussard proposed an original way to solve the mass problem by avoiding carrying the necessary propellant. Thus was born the concept of the interstellar ramjet, a vehicle capable of collecting the hydrogen present between the stars as it traveled and harnessing it in a nuclear fusion engine. But apart from the problems presented by making the actual engine, collecting interstellar hydrogen would be anything but simple. In fact, assuming an average density of 1 atom per cubic centimeter, to collect 1 kilogram of hydrogen at 1/10 the speed of light would require a huge funnel with a mouth over 5,000 kilometers in diameter, and the matter collected would still be negligible compared to the needs of propulsion. This is why interstellar ramjets, in their various proposed versions, are not considered physically feasible. In the 1970s, the British Interplanetary Society conducted a detailed study of a variant of the Orion design, called Daedalus, under the leadership of British aerospace engineer Alan Bond. It is perhaps the most realistic interstellar ship design conceived to date. Instead of nuclear bombs, the Daedalus was to make use of a series of micro-explosions produced by nuclear fusion of small deuterium and helium-3 tablets. The fully automated, 2-stage spacecraft would have been able to reach 0.1 c, 10% of the speed of light, with a mass at the departure of 50,000 tons, 93% of which was propellant. This would have enabled it to reach Proxima in just over 30 years, then transmit the information gathered during the flyover back to Earth. Another promising proposal is the StarWisp laser sails, where the problems of mass and heat are solved by eliminating the engine, replaced by the pressure exerted by a beam of radiation directed onto a very light sail. However, the problem of energy and also that of travel time must be addressed with highly innovative solutions. Since the original idea was formulated in the first half of the 1980s, the interstellar sail concept has undergone several reworkings and improvements, mainly to limit the energy requirements of the voyage and to make its operation more plausible. In any case, the main elements of the system would consist of a very powerful laser or microwave transmitter, probably placed in space, a giant lens, used to concentrate the radiation into an extremely collimated beam even at a very great distance, and the actual interstellar sail, capable of intercepting the radiation and being significantly accelerated by the pressure thus exerted. And when we say sail, we do not mean a racing spinnaker, but of something at least 6 kilometers in diameter and weighing only 30 grams. Accelerated to 0.2 c in just 2 weeks, StarWisp could reach the Alpha Centauri system in as little as 21 years. Another possible solution is that of antimatter propulsion. We know that 1 gram of antimatter, when converted into energy, generates an immense amount, about 70 times that produced by nuclear fusion and 4 billion times the energy produced by burning oil. Such an engine would enable us to reach about 40% of the speed of light, and the duration of a trip to Alpha Centauri would be reduced to just over a decade. However, little antimatter exists in nature now, and it is not easily captured. It is therefore necessary to produce it, which is done in infinitesimal quantities in large particle accelerators. Making engines specifically for space exploration, however, would require several grams of it. This sounds like nothing, but it is a vastly greater amount than has been synthesized to date. Just think that an accelerator would have to run its antimatter factory for about 1 billion years to produce a single gram of antimatter. Even if we imagine technological innovations such that this immense time would be cut down, the conventional energy required to produce a couple of grams of antiprotons per year would be equivalent to a total energy consumption corresponding to about 50 billion watts, equal to the power output of all U.S. nuclear power plants. Here, this is currently our situation. We want to go and see the planet Proxima b, but we don't know how yet. Our technology is practically still in its infancy, although it is progressing rapidly. No one can predict what humans will be able to do by the fateful date of 2069, but if development proceeds at the current rate, along with many new problems to be solved, we will also have greatly increased our capabilities in precisely those fields crucial to interstellar travel. In the beginning, the missions directed to the stars will probably be conducted with intelligent robotic probes, miniaturized beyond any currently conceivable limits, capable of traveling at 0.1 c. But one need only extrapolate a little to the extraordinary progress being made in the fields of biotechnology, genetic and molecular engineering, embryonic development, and cell physiology, to realize that even with simple probes such as those, humans themselves could rapidly propagate around the galaxy, as proposed by physicist Frank J. Tipler and described by Arthur C. Clarke in the fascinating novel The Songs of the Far Earth. In practice, this would involve the creation of so-called von Neumann probes, i.e., intelligent automatons that, upon arriving at their destination, would be able to construct, from available raw materials, copies of themselves and habitats for eventual living beings, including humans, synthesized in situ from the information contained in the genetic code and instructions for the generation and development of embryos. Having successfully initiated the colonization of a world, von Neumann's probes could then build new interstellar spaceships and automatons, destined to take the flight to other star systems to repeat the feat. Of course, we are talking about small probes. Interstellar travel with humans on board, and NASA will have to take this into account, would be enormously more complex, involving mass and energy scales thousands to millions of times larger. What can be conceived with current knowledge points us back to the idea of interstellar arcs, giant ecologically self-sustaining habitats capable of roaming the stars for thousands of years as countless generations of humans, animals, and plants follow one another within them. These arcs could be built on the model of the giant space colonies studied by physicist Gerald O'Neill in the 1970s, and then launched into interstellar space even at modest speeds of less than 0.01 c. But it is difficult to imagine under what conditions and for what reasons human beings should undertake a journey knowing already for certain that they would never reach their destination. Probably, only the progressive uninhabitability of our own and other solar system planets, colonized in the meantime, could induce many to that extreme choice. The discourse would change drastically if it became possible to significantly extend human life, or slow down metabolic processes during travel, while being able to reach, with the large spaceships required, at least speeds between 0.1 and 0.3 c. But for this to materialize, it will probably have to take several more centuries unless physics still holds some incredible surprises in store for us. How then will NASA make good on its promises? May it have an ace hidden up its sleeve? Don't worry, we'll just have to wait until 2069 to find out.